Dear colleagues, this seminar is normally chaired by Professor Drensky. However, he is now simultaneously in one more meeting, so I will do this office today. So it's my pleasure to announce that today's speaker is Valentin Iliev, and the title of his talk is on the degree of dependence of two events as a relative invariant of the dihedral group of order 8. Valentin, please.
Thank you, Mitko. Thank you. I'll share the screen first. So first, thank you for everybody who is my guest here. Last lecture on May 21, I invited many specialists in probability theory, but nobody attended my lecture. Now I'm happy to see at least one. This is my friend Dancho. This is Professor Dan Stoyanov from University of Newcastle in England. So I'm happy to see him. Let's begin. I'll make a review of the previous lecture from May last year, because this text is not in the textbook yet. I'm joking, of course, but it is necessary to remind you the definitions and the construction of this degree of dependence. This is the abstract. I think you read it in the announcement. I'll begin with some terminology. I call an ordered pair of events in a probability space Yule's pair. The reason you'll see the reason in the end of the talk. This is a historic reason. This English statistician George Yule, who first considered two attributed tables, and this is equivalent that you consider ordered pairs of events in a probability space. So we denote by alpha the probability of A, by beta the probability of B, and we call this a Yule's pair of type L alpha beta. And any such pair using Kolmogorov's terminology produces a partition of the sample space of that probability space. And in accord with Kolmogorov terminology, this is called experiment. So this two attributed table reflects the probability of the results of this experiment. Here, this is the probability. C1 is the probability of the intersection of A and B. C2 is the probability of intersection of A and the complement of B. And similarly, this is the probability of the complement of AC and B, and AC and BC. Here are the formal definitions. And the cornerstone of this work is a very simple observation. C1 plus C2 is equal to alpha here. C3 plus C4 is equal to 1 minus alpha. This is if you read the rows. If you read the columns, C1 plus C3 is beta, and C2 plus C4 is 1 minus beta. So we get a linear system that whose general solution is a straight line. This is the form of the general solution. We choose C1. This is the intersection of A and B, the probability of the intersection of A and B as a parameter. Then all other components of the probability distribution are expressed in this way. And obviously, the sum of all probabilities is 1 because this is a partition of the sample space. And something more, if you consider not only theta, but also alpha and beta as variables, you get a map iota from R3, this is the three-dimensional real space, to H. This is the hyperplane in R4 with this equation. And this line, of course, lies in this hyperplane. So we can define this iota, this map from R3 to H, using the formulas from here. And you get in this way an affine isomorphism with inverse affine isomorphism kappa, which is from H to R3, that has this form. This can be found immediately from the system. So this is an affine isomorphism iota. And on the other hand, the trace of the four-dimensional cube, all those Xi, Xi1, Xi2 up to Xi4, such that they are between 0 and 1, and its trace on the hyperplane H is the three-dimensional simplex. This is the well-known object from any theory, almost any theory, touches this object called three-dimensional simplex. This is a tetrahedron. I called it delta 3, and it is defined in this way. This is defined in this way. And the inverse image of this tetrahedron delta 3 is, of course, another tetrahedron T3, I denote it by T3, and translating those formulas in the language of alpha, beta, and theta, you get this. You get this. And in other words, this is the tetrahedron with vertices 0, 0, 0, 1, 0, 0, 0, 1, 0, and 1, 1, 1. And this is this tetrahedron. And it turns out that this tetrahedron is the classification space of all triples alpha, beta, theta. This means all possible pairs, all possible Yule pairs or ordered pairs of events with intersection, with probability of intersection theta. This is that geometrical classification space of those pairs. And this system, I mean this system, 5, it yields the following, that theta belongs to this closed interval I alpha beta, where I alpha beta is has endpoints L alpha beta, R alpha beta, and here are those endpoints, the maximum of 0, alpha plus beta minus 1, and R is the minimum of alpha and beta. So we have that the product alpha beta is in this interval, and we denote by in this way, interior, the interior of the interval I alpha beta. So we have this lemma, which is automatic, almost automatically can be proved. The following three statements are equivalent. Alpha beta is in the open, the square of the open interval 0, 1. This means alpha and beta are strictly between 0 and 1, both. And the other equivalent statement is that alpha beta, the product, is in the interior, and the third equivalent statement is that the interior is not empty. And under these conditions, all CKs are greater than 0, and vice versa. If there exists theta such that CKs are strictly greater than 0, then those three statements called equivalent statements hold. And you have this stratification of the corresponding tetrahedron T3. This is a stratification into segments, line segments. And the interior has a similar stratification, but here alpha beta are strictly between 0 and 1, and here you have the interior of this line segment I alpha beta. And you get immediately a theorem that characterizes where those coordinates, C1, C2, those components of the probability distribution are 0. Here is this complete description. There are zeros on the sides of the tetrahedron and on its edges. We throw out, of course, the vertices. So we have now we take alpha beta to be strictly between 0 and 1. And remember, although all the other two statements are equivalent, and under these conditions, all ck's are greater than 0. So all ck's are greater than 0 for theta, which is in the interior. And this probability distribution has Boltzmann-Shannon entropy. It is defined in this way. This is taken from Shannon's book, in the first Shannon's paper, two Shannon's papers in information theory from 1948. And also this is from statistical physics, of course, this formula. And we have the following theorem that describes the behavior of that entropy function. Its derivative has this form. The function from this, it follows that the function is strictly increases on this interval from the left-hand points to alpha beta, and decreases from alpha beta to the right-hand point, but excluding those endpoints. And it has a global maximum at the theta, which is alpha times beta. And then the function can be extended uniquely as a continuous function on the closed interval I alpha beta, which strictly increases on this interval and strictly decreases to the right. And moreover, there exists such a symmetry. A alpha beta is E beta alpha. So this theorem can be proved as an exercise in calculus. It's easy and shows that everything is okay. I mean, I'm on the right track. This theorem, the theorem that I'll formulate now, is the first step toward the motivation of the use of Boltzmann-Shannon entropy of the probability distribution, C1 up to C4, as a measure of degree of dependence. And this theorem is from it concerns a sample space with equally likely outcomes. And you suppose that alpha and beta, the probabilities of A and B, those events, are strictly between 0 and 1. And then this equivalent class of Yule's pairs, A, B, of type alpha, beta, alpha times beta, this is theta is equal to alpha times beta, consists of all pairs A, B, of this type alpha beta, which are independent. And please note that alpha beta is the maximum of the entropy function. The entropy function attains its maximum at this alpha beta. Now, the equivalent classes of those pairs are A, B of type alpha beta, L alpha beta, this is the left-hand point of the interval, consists of all pairs of type alpha beta such that either A is a subset of the complement of B, or the complement of B is a subset of A. So this is the maximal negative dependence. We can call this maximal negative dependence. So this happens in the end point of the interval, left end point of the interval. And at the end, right end point of the interval, the equivalence class where R is the right point of the interval consists of all pairs such that one of the events is a subset of the other. So this is extreme positive dependence. Now, from the previous theorem, we get this corollary This just expresses that at theta, at alpha beta, alpha times beta is the global maximum of the entropy function. This is equivalent to theta to be alpha times beta and so on. Though this is a formal statement. And the previous theorem, the corollary, and this theorem about sample spaces with equally likely outcomes motivate the use of the entropy of a Yule's pair AB as a degree of dependence of the events A and B. And we normalize the entropy function by composing the functions E alpha beta theta and 2 E alpha beta at the point alpha beta minus E theta on the intervals of their increase. Let's see the drawing. I'll go back. This is a particular case of the entropy function, E capital alpha beta. So it increases from the left point till alpha beta. Here is the maximum. And after that, it decreases to R alpha beta. So we draw here a tangent line at the maximum. It's horizontal. And reflect the right branch of this function on this with respect to this tangent line. And after normalizing this, the function thus obtained, we get just the graph of the dependent function E small alpha beta. It takes value -1 at the left endpoint of the interval. It takes value 0 at the point alpha beta. This is the maximum. And it takes value 1 at the right endpoint. In this way, I mimic the regression coefficient, its behavior in probability theory, which is a consequence of the Cauchy-Schwarz inequality, by the way, from linear algebra. So we normalize this entropy function in this way. I express this. You see this geometrically, and get a function E alpha beta from this interval I alpha beta to the interval onto the interval -1, 1, which is a continuous function, and it is an increasing function. So E alpha beta is E beta alpha, and this value at the point theta, which is just the probability of the intersection of A and B, is said to be degree or coefficient of dependence of the events A and B, with alpha equals the probability of A and beta equals probability of B. This function strictly increases. We discussed this from -1 to 1, and has value 0 at alpha beta, exactly where then entropy is maximal. Intuitively speaking, this means that there are no relations between the events A and B. So this terminology, event A and B are said to be negatively dependent if theta or C1 AB is less than alpha beta. This means to the left part of the graph of the dependence function, degree of dependence function, and positively dependent if it is greater than alpha beta, and when theta is exactly alpha beta, the events A and B are independent. Here the entropy is maximal. And some non-formal remarks: in a small neighborhood of the left hand point of the interval A alpha beta, the dependence is negatively strong. This means it with maximum 1, this is at theta, which is L alpha beta. And in a small neighborhood of the other point, it is positively strong with maximum 1 at the right hand point. So in both cases, the entropy is minimal in a small neighborhood of the product alpha beta. And the events are A and B are almost independent. The entropy is close to its maximum. So the entropy expression of the entropy function is a particular case of what Shannon called the entropy of the joint event. Here are the graphs, we discussed them. And now I'd like to remind you some applications. By the way, I began this work, the work on this topic. I discussed this during the last lecture, trying to improve a wrong problem in the textbook in elementary statistics here in this university. And now this was a problem discussing the screening tests. That's why I would like to remind you of this notion. According to the Merriam-Webster dictionary, a screening test is a preliminary or a bridge test intended to eliminate the less probable members of an experimental series. Here, translating into the language of probability, you have sample space with equally likely outcomes. Some members possess a property and in this way form an event A. On the other hand, there exists an event B consisting of all outcomes which as if have this property after conducting the test. Thus, we obtain a Yule pair of events in a sample space omega in this way. So we know very well in practice that this the test does not always work perfectly. Sometimes it is negative under the condition that the property is present. This means it is false negative and sometimes false positive, defined in the in a similar way. So suppose that all members of the population are tested, and the probability of A is alpha, probability of B is beta, and alpha beta are between 0 and 12. This Yule pair produces the experiment which we considered, and C1 up to C4 are the results of this experiment, and the probability F minus the false negative result can be expressed in this way. This is alpha minus theta over alpha, and the probability of false positive test is beta minus theta over 1 minus alpha. And this product of both probability negative, false negative and false positive probabilities is a quadratic function which strictly decreases on this interval I alpha beta and assumes value 0 at its right point endpoint R alpha beta. So in particular, for the complement of any open neighborhood of R alpha beta in the interval I alpha beta, there exists a positive constant K such that the product of false negative and probabilities of false negative and false positive result is greater or equal to this positive constant. In other words, both F minus and F plus cannot be simultaneously as small as we want. This is a kind of uncertainty principle. We discussed last May that I uploaded this in archive of Cornell University, but this work was rejected. Well, I continued to work nevertheless and uploaded it in ResearchGate, but this is another story. So the conditional probabilities F minus and F plus are statistically acceptable in a small neighborhood of the point R alpha beta, at least one being 0 at this point. So this is there is a way for the test to be precise, and this is when theta is in a small neighborhood of the right endpoint of this interval. The reliability of F minus and F plus decreases when theta approaches the left endpoint of the interval, and when theta is the left point of the interval, at least one of those probabilities is 1. This means that it is completely unreliable, not reliable. So I'll omit these trivial considerations about the behavior of the degree of dependence functions. And now let's consider another topic, effectiveness of a vaccination. Let's consider a population whose members have a particular disease for which a vaccine is developed. And let A be the set of all those who have recovered, and let B be the set of all vaccinated members. Then AC is the set of all fatal endings, and BC is the set of unvaccinated. If alpha is the probability of A, beta is the probability of B, then the degree of dependence of the events A and B measures the effectiveness of the corresponding vaccine. So if it is close to -1, then the vaccine is counterproductive, and its effectiveness increases, being negative when the degree of dependence is negative, and positive when it is positive. In case it is 0, the vaccination does not influence the recovery. And it is very positively effective when it is close to 1, the degree of dependence. And I took this from memoir of this English statistician, Yule, from 1912. He presents a table below in order to show the recoveries and deaths among vaccinated and unvaccinated patients during the smallpox epidemic at Sheffield in 1887-1888. As far as I know, Sheffield is a small town it was a small town in South England. I'm not sure. Okay, these are the results are represented in this two attributed table. And here alpha is 0.88 and so on, beta is 0.89, theta is 0.84, and the degree of dependence is 0.26, so about 0.27. So the results of this vaccination during the epidemic are faintly positive. The recovery is not only due to vaccination. By the way, George Yule invented his own index of association of these two attributes of the table, and his index shows 0.90 effectiveness. By the way, we can make infinitely many such functions that have those three properties. Zero to the left is -1 alpha when the events are independent, it is 0, and when they are extremely positive dependent, it is 1. You can construct infinitely many such functions. But I don't believe that his index is precise. I believe in my index. Why? Just because of the next consideration. If you consider this Yule's pair as a screening test, it has a statistically acceptable false negative probability. It is 0.0482. This means the probability that a member is unvaccinated under the condition that he is or she is recovered. This is an acceptable probability. But on the other hand, this false positive probability, it is about 50%. This means that this is the probability that a member of the population was vaccinated under the condition that he or she is dead. This is terrible. This is terrible. So half of the dead are vaccinated. And both arguments support the opinion of Andrei Ciurbanul, this is a professor at the Department of Immunology at the Institute of Microbiology in Bulgarian Academy of Sciences, that the vaccination must not be made during the epidemic and has preventive character only. And indeed, in the period from 1958 to 1977, the World Health Organization conducted a global preventive vaccination campaign that eradicated smallpox. This is the only illness who was eradicated. This means that the vaccination has preventive character only. And moreover, here I considered previous work that was cited by George Adnaeul, the work of MacDonald from 1902, where he considered the epidemic in smallpox in 6 English towns. Among them is Sheffield, and this example was taken by George Adnaeul. And for almost all, for 5 of those towns, my index, my degree of effectiveness of vaccination is 0.60, 0.26, 0.27. This means faintly positive influence. You have to take into account this is the general vaccine. It is at that period at most at about 100 years old. And there is only one town. I don't remember its name, but everybody can see it in the paper of MacDonald, in which the author notes that the vaccination was not made, was not applied several years before the epidemic. And what is very important, my index, my degree of dependence shows here 57% of positive influence of the vaccination on the recovery, This means, once again, this confirms this statement that vaccination has preventive character only. But unfortunately, I'm sure that there are many statistical data in English archives, but I cannot read them. So to make a more precise picture of this. Now, let's consider this from the point of view of information theory. This experiment, which was considered in the beginning, is the joint experiment of 2 simpler binary trials. This is A united with AC and B united with BC, with this probability alpha and beta. Then the average quantity of information of one of the experiments A, Gothic A and B, relative to other. This I read this from one paper of Gelfand, Kolmogorov, and Yaglom. It is defined in this particular case by this formula. Here, this formula is in this particular case. And then the definition of the degree function, E alpha beta, and this formula yields the following. The average information of one of the experiments A and B relative to the other, this is denoted in this way, at the point theta is just the the deviation of the entropy from its maximum. The deviation of the entropy from its maximum. And from here, and from the construction of the dependence function, E alpha beta, you get those formulas for this dependence function. And it can be written in the following way. This is here the information, the average information over minus the average information over the maximum of the average information to the left of the interval, from the left point to its maximum. And here is again the information, the average information divided by the maximum on the points to the right. And these 2 formulas show the very important corollary, imply very important corollary. The degree of dependence of 2 events does not depend on the choice of unit of information. The unit of information is, by the way, the base of the logarithm. So it doesn't matter if those are bytes or nuts or any base, which is important property. And now let's begin with the second part of this work. And it begins, first we define this notation. This is A diamond B. This is the complement of the symmetric difference. And I began to ask how many pairs, ordered pairs of events in the Boolean algebra produce the experiment, a given experiment. It is naturally identified with this partition of the sample space. And here is the answer, very unexpected answer, very simple, by the way. Its proof is purely combinatorial and can be made by considering different cases. Here is the sequence of those pairs that produce one and the same experiment that corresponds to the pair AB. This is the AB itself, and here here are the types of the corresponding pairs. AB has type alpha, beta, theta. Theta is the probability of the intersection of A and B. And then ABC has this type, alpha, 1 minus beta, alpha minus theta. ACB has this type, 1 minus alpha, beta, beta minus theta. And in this fashion, I list 24 powers, 24 pairs, Yule's pairs of events that produce one and the same experiment. And unfortunately, of course, you can see immediately that in general, I mean, those Yule's pairs are not necessary to be different. It's not necessary to be different. But we can find a condition under which they are pairwise different. And this is the way of doing this. It is enough to show that for some alpha, beta, and theta, those types are pairwise different. Then the corresponding pairs are pairwise different. So, and this is part of real algebraic geometry. We take the set of 4 points alpha, beta, theta in R3 in the three-dimensional real space, where the types from the are pairwise different. This is semi-algebraic, open and three-dimensional. Semi-algebraic means that it is defined by inequalities. And here, all inequalities are strict. That's why it is open. Moreover, it is three-dimensional. And it's, if you consider its trace U3 on the interior of the classification tetrahedron T3, it is not empty, this intersection, because otherwise the interior would be a subset of finite union of planes. This is impossible, of course. So this union is not empty. And then the theorem, a theorem from a book in real algebraic geometry, assures that, guarantees that the open two-dimensional projection U2 of U3 onto alpha beta plane is semi-algebraic. And then openness means with respect to the standard topology in the three-dimensional and two-dimensional space, respectively. And under some plentifulness condition on the Boolean algebra A, for example, if it is non-atomic, then there exists plenty of Yule's pairs AB of type alpha beta in U2. And in this case, our sequence consists of, is in fact a set coincides with its associated set. It consists of 24 pairs. So in general, we may say, in general, this sequence is a set. And now let's consider the set of all experiments in the probability space omega A. This is the function of probability. This is a measure. The set of all, this means the set of all finite partitions of omega with members from A. And then this rule, obvious rule, defines a map from the pairs to the set of all partitions. And our lemma, previous lemma, says simply that the inverse image of this image of this I alpha beta, sorry, coincides with the associated set of the sequence from lemma 8. So we denote by I alpha beta, AB, the set of equivalent classes in A2 of the form alpha beta theta, which contain the members of this inverse image. So here I repeat once again how to get the types. Here, if AB has type alpha beta theta, then ABC is a pair of type alpha 1 minus beta alpha minus theta, and so on. So now the next step is to consider those alpha beta not only as probabilities, but as the coordinate functions in R3. Then the members of I, alpha beta, produce a set S4 consisting of 24 affine automorphisms of R3 from the following set. Here are the left-hand side. These are the automorphisms are written in terms of coordinates. These are the types of the corresponding pairs that produce our experiment. And here you have 24 pairwise different automorphisms, and they are indexed here by the permutations sigma from the symmetric group S4, just because of the theorem below. The theorem, we already see the theorem below. The operator of symmetry, sorry, sigma from H to H permutes in this way the components of the probability distribution. And we have the following theorem. We have this commutation property. This iota composed with phi, this automorphism phi sigma indexed with sigma inverse is equal to sigma composed with iota. This is a commutative diagram, but I couldn't draw this diagram here. I had no time to do that. And the map, this map from S4 to the group of all affine automorphisms of the three-dimensional space R3, this map given by this formula is group anti-monomorphism with image Gothic S4. And 3, the group Gothic S4 is the affine symmetry group of the classification tetrahedron T3. And well, I'll omit the proof of this. So let's write down the affine isomorphism phi sigma in terms of the coordinates in R3 in this way. And we obtain that phi sigma, sorry, maps the components of the partition T3. You remember that this is partitioned by line segments. So it maps those line segments on the corresponding line segments of T3 also. You have to take into account the sigma, that phi sigma maps T3 onto T3. This can be shown easily. I omitted this. So phi sigma maps T3 onto T3, and something more maps any component of this partition, any component of this stratification on the corresponding stratification of T3 here. And let's set by T hat, T3 hat, the union of those strata, but you take here alpha beta between 0 and 1 strictly, but you, instead of the interior of this interval, you put here the whole interval. So in this way we can make we can approach the endpoints of this interval via theta, and we can take the limits. So we get the following lemma from these considerations. This automorphism phi sigma maps the set of endpoints of the segments alpha beta I alpha beta onto the set of endpoints of their images here. And you have phi sigma is T3 hat, phi sigma of T3 hat is T3 hat. This means T3 hat is closed with respect to this, to all automorphisms. And now using the anti-monomorphism from the previous theorem, the group S4 acts on the real functions on R3 via the rule sigma dot f is f a circle phi sigma inverse, and we consider the following function on the three-dimensional simplex, the interior of the three-dimensional simplex delta 3. It is defined using the formula for the entropy, and then after composing with the iota, you get our entropy function E capital. Then this function G is continuously differentiable on the interior and can be extended under the name G hat as continuous on delta 3 hat, which is the image of via iota of T3 hat. And then the function E is continuously differentiable on this interior. It can be extended under the name E hat as continuous on T3 hat. And this is, you can mimic the theorem for our function E alpha beta theta from the previous lecture. So we have all natural properties satisfied, and you get that by the way, we throughout the end of this work will with the abuse of the language, we designate G theta via G and D theta via E. So we consider the extended functions. And here we have a theorem which can be proved easily. I omit the proof. This function, the entropy function, is defined on T3 hat, is an absolute invariant of the symmetric group S4. And now we take alpha beta to be strictly between 0 and 1, and define this function E alpha beta theta in this way. We are using here the definition of the corresponding degree of dependence of the events A and B. So this is the degree of dependence written in another way. And let's consider the dihedral subgroup D8, it is generated by these two permutations, 1, 3, 4, 2, and 1, 4 in S4. And this is one of the 3 Iliev 2 subgroup of S4. And we define by, we denote by chi abelian character of D8 with kernel, the group of order 4 generated by these two transpositions, 1, 4, and 2, 3. It has image 1 and minus 1. And then the theorem says that the function E from the previous formula is a relative invariant of weight chi of the dihedral group D8. So this is the result, and the result uses some properties of this subgroup D8. One of the three Iliev two subgroups of S4, namely that for any member of D8, the main point is this: for any member of sigma of D8, phi sigma at alpha beta is equal to alpha sigma beta sigma and the product alpha sigma beta sigma. So this is the main property, and this allows us, and other properties that well depend on the fact that sigma is in the subgroup K, which is the kernel of our abelian character, or outside the kernel. We are using those properties to show that indeed sigma dot E is equal to chi sigma times E. This for all permutations sigma in D8 in the dihedral group of order A. And this means E is a relative invariant with weight chi of the dihedral group D8. And we get immediately, this can be translated into the following formulas for E alpha beta. Here are the symmetry formulas for alpha beta. So this is just a translation of the fact that E alpha beta is a relative invariant of weight chi of D8. And the history, a similar setup was used meticulously by George Yule in his memoir. This is the title of the memoir, in order to classify the object of individuals observed into two classes only. So I gave the name of those ordered pairs Yule's pairs in honor of George Yule, because he did systematically, he did a systematic study of the two attributed tables, which is equivalent to study of Yule's pairs. And he noted that McDonnell, in one earlier paper from 1902 in Biometrica, he used the two attributed tables as a tool to study the degree of effectiveness of vaccination in smallpox in those 6 English cities. So there are other indices of dependence. Some of them are invented by Nicolo Breshko, the Bulgarian mathematician Nicolo Breshkov. This is the index. This is the measure of association of George Yule. I discussed this. We can construct infinitely many such functions. Here are the graphs of this is the Obreshkov coefficient of regression of B with respect to A. This is not symmetric function. It has also those properties between -1 and it is 0 and B and A and B are independent. Here is a comparison of my degree of dependence with Obreshkov degree. So all those functions are linear functions, in fact. And here is his coefficient of correlation between A and B. It is symmetric. And here is its graph. So I would like to know that Boyan Dimitrov meticulously studied the above measures of dependence, I mean measures of Nikolov Breshkov in his paper, which is cited here. So this is what by Nikolov Breshkov from his textbook. For a complete characterization of the dependence between two events A and B, one needs to know 3 of the 4 probabilities. This means 3 of the 4 Xi1, Xi2, Xi3, and Xi4. So thank you very much for your attention. And by the way, I'd like to thank Boyan Dimitrov from Kettering University in Michigan, United States, and because his notes and suggestions were very useful for me for the first part of this paper. And I would like to express my thanks to Dmitry Gelev, who for sending me the references to the works of Andrei Nikolaevich Kolmogorov on information theory, and Hristo Iliev by his mastery of drawing the graphs. And also the administration of the Institute of Mathematics and Informatics of the Bulgarian Academy of Sciences for creating perfect and safe conditions for work. I'll also offer my heartfelt gratitude to the moderators from Archive because they simulated my interest to study and generalize the properties of a screening test up to this work. Thank you very much. Here is the bibliography. Well.
Okay, so let's thank Valentin for his talk. And are there questions, comments?
I have maybe a stupid question, but let me ask it. So on one of the first slides with Yule's theorem, if you go to that theorem, you had 4 cases or 3 cases. And so you were saying either A is contained in the complement of B, or B is contained in the complement of A, but these 2 are equivalent, so it's enough to say one of them.
Okay, okay.
It's trivial.
I understand, yeah, I know.
It was a stupid remark.
For completeness, yeah. Yeah, thank you, Dikra.
You're welcome.
More questions? More comments?
Value, you are probably studied also, you see the relation with Heisenberg uncertainty relations. I think that you mentioned this to me in early stage.
Sorry, once again, Todor,
Heisenberg uncertainty relations.
Yes.
Have you look at this more? I mean, in some examples, I guess if you have 2 oscillators, you can somehow match to your scheme.
I stated this uncertainty principle for screening tests to show that in general, this means in a neighborhood, complement of open neighborhood of the right endpoint of the interval, there exists a positive constant such that the product of false positive and false negative is greater than this constant. This means that both cannot be simultaneously small. But I cannot extend this to, I'm not able to do that for some other cases, if you are asking this. What's your question once again, Todor? I didn't understand. So you appeared, sorry, you disappeared. Todor. So Todor was like the phantom in the opera.
Todor is somewhere
In the mountain.
in the open, so he's not in a building. Probably the connection was changed. Yep.
Okay. So I didn't understand his question really.
It was more of a remark, I guess. Yeah. More questions? More comments?
I have just a request. If I can have these slides, because at some point my battery was down, so I lost connection. So I lost somehow the connection with the vaccine, etc. It's highly interesting to me. So,
for one thing, we are recording this talk and it will be put on the web. Also, the slides, we are to ask Valentin to give us the slides, and we probably put them on the web as well, on the page of the seminar. Yeah, here is Todor back. Todor is back now.
Give me your email and send you everything.
okay.
Todor, you are in the mountain or where?
Yes.
Todor, turn on your microphone.
Yes.
Sorry, I had an accident with the battery of my computer. So, well, we will meet and discuss more. It was many. I think that there's some potential applications to another context.
I don't know how to apply them in physics, so I'd be grateful.
Thank you. Thank you for your talk.
Well, in the uncertainty principle, I think this is the trace of some commutator of some Hilbert space operators, but
yes,
here
you
we don't have
some,
anything like that.
Right, you don't have, but we can think about a scheme that can come close to that situation.
Yeah.
Okay, I'd be very glad to discuss with you, Todor.
Thank you, Valio.
Now, more questions? More comments?
There is one chat.
Yeah, so I can see Ivan now. Ivan, are you preparing to ask a question? Your microphone is off.
Microphone is.
Ivan, turn on your microphone, please.
Thank you for the talk, for the interesting talk, and I have to leave for the Scientific Council's meeting.
Thank you for being here. Thank you.
So if there are no other questions, then I will just stop recording